Let's resume with Agnese Pacifico, yes, Agnese Pacifico from Università La Sapienza di Roma. And she will be talking to us about an algorithm for the LQR problem with partially unknown dynamics. And so, without any further ado, I will try to make them work. And you can talk.
Okay, thank you for the introduction. This talk is about joint work with Andrea Pese and Maurizio Falcone. This is the outline of the talk. First of all, I'm going to present the problem we want to solve. Then I'm going to describe the algorithm we proposed to solve this problem. And finally, I will show some numerical tests. So let's start with the problem. First, let me recall what a classical linear quadratic regulator optimal control problem is. We have an n-dimensional vector that depends on time, that is our state, and it follows these dynamics, which is linear, because A and B are matrices. A is an n times n matrix, and B is an m times n matrix, where m is the dimension of this other vector u, and u of t is a measurable function that we can choose, and we call it control. And this is just the starting point. To this equation, we associate a cost functional that contains only quadratic terms, so we call it a quadratic cost functional. And our goal is to find a measurable function u that minimizes this cost in the class of all admissible controls that are these Lebesgue measurable functions. Observe that a good control will make this low, so we expect that our optimal control brings the solution near to the origin, and otherwise this cost would be high. In case where there is this simple dynamics and all the matrices appearing here are known, so the dynamics is known, we have a solution for this problem. So we know that the optimal control is given by this expression, where R and B are matrices appearing in the problem, and P of T is a time-dependent matrix that is solution to this metric differential equation that is called the Riccati differential equation. And then this is just the state of the system, and that's why we call it a feedback control, because it depends on the state. The problem we want to solve is a slightly different one, because we take the same dynamics as before and the same cost, but now we assume that the matrix A, that here I represented in gray, is unknown. So the same as before, but without knowing the matrix A. And of course we cannot find the optimal control now because we don't know the matrix A, but we have a new goal. So we want to approximate the matrix A, and at the same time we want to find a low-cost control. Here I wrote that a low-cost control should bring the system towards the origin because of what I observed before about what we expect from good control. And furthermore, we want to do this using only one simulation, and by this I mean that we cannot observe the system behavior in advance. So we have to start controlling the system while the A is still unknown and while we are still approximating it. So for the algorithm, we of course need to discretize the time interval. And so we divide our time interval into rounds, and then we divide each round into smaller time steps of length delta t. And we call Ti the endpoints of each round. And we denote by Tij the jth point in round I. The algorithm is based on this idea. First, we want to build a probabilistic model of the dynamics, and we want to use this model to construct the control. But we cannot build the model before and then construct the control, but we have to do these things at the same time, in some sense. Indeed, we will carry out two major operations for each round. At the beginning of each round, we have a probability distribution over matrices that represents our knowledge of the matrix A at this time. And this is given by the previous round, apart from the first step from the first round, where pi 0 must be chosen by us. And the first operation we do is we find a control that we use just in round I, and we find this control by using the mean matrix of this distribution and solve the Riccati differential equation using that. So then we apply this control for all the time steps in round I, and so we can observe the trajectory that the system follows, and thanks to this we can build a new probability distribution pi I plus 1, and then this pi I plus 1 will be used in the next round to construct the control for the next round. This is the algorithm written in a bit more detail. First, we discretize the time interval, then we choose a distribution pi 0 to start with, and then we repeat these operations for all the rounds. First, we find the control UI star, as I said before, using the mean matrix AI bar of the distribution pi I. Then we use this control for all the time steps in the ith round, and then we observe the trajectory and use these observations to construct the distribution pi I plus 1. I mentioned that we need to choose pi 0, and we chose it in this way. We suppose that A is made of all these rows, and each row of the matrix A is distributed as Gaussian with some mean m0 and covariance matrix sigma 0. And this is how we chose m0 and sigma 0. Of course, if we have, for some reason, some information about the matrix A, we can encode it in this prior distribution. Then, another point I mentioned is that we have to gather data and use them to update the distribution. So, what we do is we observe the system states for all the times of the round, and we know that they follow these dynamics. Then we call just xij the point, the state of the system at the time tij, so in round I, the jth time step. And if we take this expression, we rearrange terms and we approximate this derivative, for example, with a first order scheme, we obtain this expression, and we call yj, this right-hand side here, and we notice that everything in this part is known, so we can compute this. And of course, this is not exactly equal because we approximated the derivative. And also because maybe there is some noise on observations, so maybe this observation could be not exact, but for the moment we can observe that this is an approximation, so it's not inequality here. So we consider this yj as a noisy observation of this product of the matrix A times xij. And so the kth element of this vector is the kth row of the matrix A times the vector xij plus some noise epsilon, which is Gaussian. We assume it is Gaussian. So given that, now assume for a moment that pi I is of this form, so in the same form as the pi 0 shows. In this case, we can define X as this matrix whose columns are these observations of the state for all the times of the round. Y is this vector, which is made of all the kth components of the vectors yj that appeared here in the previous slide. Of course, this must be done for each k that goes from 1 to n, so for all the rows of the matrix. And in this case, we can apply some variation formulas, and if we take this as a prior distribution and we use this assumption, then we get that our posterior distribution is of the same form of the prior and has this mean and this covariance matrix. Since we started from a prior distribution of this form, then we will always find a distribution pi I which has this form, and so we can always apply this formula, and so this assumption is always satisfied. So this is how we update our distribution over matrices. And finally, I'll show some numerical tests. This is the first simple test where we are in dimension 2. So the x is a two-dimensional vector and the control is one-dimensional. This is the same problem we proposed before, just we fixed these parameters. And the matrix A is this one, but of course it is unknown to the algorithm. And this table shows some results. We have different values of delta t, and for each of them we use our algorithm to find the control it can find. We also knew the matrix A, so we could also compute the optimal control and so the optimal cost. Here there's the error between the cost computed by our algorithm and the optimal cost. And we can see that if delta t goes to 0, it decreases, the error decreases with order 1. And these plots are for the same delta t's in the previous table. The blue line represents what we can do knowing the matrix A, while the red line is what we get with our algorithm. So this is the control, the optimal control is in blue, and the control we can find is represented in red. Of course, at the beginning we don't know what the matrix A is like, and so they can be different, but we can see that if we take smaller delta t, these controls are very similar to each other, and also the trajectories. Here in blue there is the trajectory that the system follows using the optimal control, while in red there is the trajectory that the system follows using our control. And so we can see that if delta t goes to 0, also the trajectory is more and more similar to the optimal trajectory. And this is just another similar test, just with dimension 4, and the control is in dimension 3. This is the cost, the optimal cost, and this is the cost obtained by the algorithm. And these are the three components of the control. Always there is in blue the optimal control, and in red the control found by the algorithm that doesn't know the matrix A. And this is for the same test, representation of the trajectory. Of course, it was a trajectory in R4, so I represented just some projections in couples of some components of it. This red point is the starting point of the trajectory. We can see that at the beginning the two trajectories are not the same, because at the beginning we don't know what the matrix A is, and so we can choose wrong controls. But then we notice that in the end, also our control is able to bring the system towards the origin, and that was one of our goals. To conclude, I presented an algorithm for the linear quadratic regulator problem, and it is an online algorithm because it approximates the dynamics and the control at the same time, and so these two operations are using only one simulation. That is what we wanted. Because we assume that we cannot observe the system behavior in advance. And so, thank you for your attention.
So, thank you. This is working, wow. Thank you, Agnese, for the presentation. And are there any questions in the room? Okay, so this is one. I will bring the microphone. Stop it to work so you can go without.
Yeah, it's fine. Can you go back to the slide where you were approximating the derivative? Yeah, that one. I don't understand. You said everything on the right-hand side is known. I don't understand why xj plus 1 is known.
Okay, because we observe all the x, all the trajectory points for the round I. So we know all these x at all the times at round I. So we know x with subscript I and each superscript that goes from 0 to capital S. So we both
first run the dynamics for the whole round.
For all the round, exactly.
And then you use the y day.
Yes.
Okay, and then just a second question, how do you solve the differential recutting?
How we solve the equation?
Yes.
Okay, there are some methods for solving it, but if you want, you can also just vectorize this equation, because it is a matrix differential equation. You can vectorize and you can obtain a differential equation with just vectors, and you can use any solver.
Yeah, of course, if you're working with a 4x4 system, not if you're working with 1,000 by 1,000.
Yeah, of course, but there are also methods for this for solving this equation.
Okay.
In our tests, we didn't try with so high dimensions, so we didn't need so very, very, very optimized code, but.
Makes sense. Thanks.
Always about the derivative that you approximate. Can you use different format with the approximation of the derivative? Maybe that they have
Yes, we can. So we used here a first order approximation, but we also tried with second order or fourth order approximations. And yes, you can. There is just one issue with that, because actually the control we use is piecewise constant, because in each small step of the length delta t, it is constant, and so the control is not regular, and but here the x depends on the control. So if the control is not regular, also the trajectory is not regular. So we cannot use the higher order approximation, or at least they are not accurate, because we don't have the needed regularity. So in that case, you need to use a control that that is more regular than this. For example, you can keep it constant for more time steps, and in that way it works, but but I mean, there is there is in some cases. In some cases it's better, but there is this issue that you have to work with, for example, a control that is constant for more steps, and so you lose something.
I see that.
So now the microphone is working again, so it's on.
In the test, did you add random noise to the observations?
No, we didn't add, but it would be interesting to try.
Okay. And about the variance of the random noise, you just fix the value?
Yes, because we know that that noise is due to the error in the approximation, and so we know that it is something of order of delta t, and so we use this information to fix this sigma square.
Okay. And also one more thing. Do you think it would make sense to do the same thing not with A but maybe with the other matrices, like for the dynamics or for the code?
With other unknown matrices, yes, we wanted to try to find also something similar with, for example, an unknown matrix P. And there are works about these, but they don't use only one simulation. But we still haven't done that, but we would like to do it in the future. Maybe it's more complicated because we use, I mean, when we write these, if also B is unknown, we have more problems, but we are working on that. So.
Okay, thanks.
Well, thank you again. Thank you again, speaker.